So, hello everyone. Now I am going to solve a couple of exercises to prove that this process here is a martingale, that this other process here is a martingale, and also that this process here is a martingale, right? Well, and for this one, I'm going to give you a hint so that you can see how to prove that a process is a soft martingale. Now, let's get started. For the first, the only thing we have to do is to see, okay, so we are defining a sequence of independent random variables. They have different means. They are all different to 0, right? And, well, we have to prove that this sequence is a martingale, right? With respect to certain sigma algebra. So what we need to do is to prove that, I'm going to insert a page in here. What we need to do is to prove that the expectation of yn say plus 1, that is y realization of the process at certain time, say n plus 1, given the story up to certain past time, in this case, say n, equals precisely the process at time n. So this is what we need to do. Now, I need to emphasize the fact that the reason for which I am writing here n, right, is that I need this to be a certain time which was before this time took place. So what I intend to do is to see that this equality holds. Now, in order to do that, what I need, this is the first exercise, what I need to do is to write what the y process is. Now, according to our definition right here, this process equals the product from 1 to n of all these random variables divided by their means, their respective means. So what I have in here is xn divided by m1 times x2 divided by m2 times up to xn divided by mn times xn plus 1 divided by mn plus 1. So what I need to do right here is to use devise certain, well, right now I'm saying device like this. So what I need to do now is to see some recurrence rule, right? So what I have in here is precisely yn multiplied by xn plus 1 divided by mn plus 1. So why is it that I need to do this? Well, because I need to find the expectation of this thing given certain story. So the story is taken up to time n. So that is why I needed to find this correspondence rule. So now I'm just going to write down the expectation of y at time n plus 1, given the story up to time, say, n. And I just wrote that this equals the expectation of yn times this, right? And I'm going to write the condition of the story, of this story. So this is just the expectation of these things here. Now, by invoking the argument of measurability, I can say that this thing is known up to time n. So that is just another way of saying that I am invoking the argument of measurability. So when you can say that if you have a story which just happened up to time n, then you know what happens with the process y, then you're saying that you are using measurability. So for that reason, now I can just write yn times the expectation of xn plus 1 given this, right? like that. And well, now I just need to see the fact that this story here just came from, all these x's. You see? Because what I'm saying is that all this story was generated precisely by these random variables. So that means that I am taking the expectation of this random variable given that a story of x1, x2, x la 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 up to xn just took place. But what does that mean? Well, in terms of independence, yes, we can argue that this thing is actually just yn times the expectation of just xm plus 1 given mm plus 1. But this is just yn divided by mm plus 1 multiplied by the expectation of xn plus 1, which by our hypothesis is just mn. That means that in here we just have mn plus 1, and this thing cancels out with this other thing, and we have exactly what we needed to prove. Okay, now for exercise number 2. Okay, here I have that they give us a sequence of independent random variables, right? And they are almost Bernoulli random variables. So as you can see, they can be worth 1 or -1 with probabilities P and Q respectively. And that happens just for all the members of this sequence of random variables. Of course, the P and the Q are between 0 and 1. And next, they define a sum, right? And a quotient, which is raised to this power, to the Snth power, right? And now they ask us to prove that yn, that is this quotient raised to this power, is a martingale with respect to this particular filtration. Now, that is also fairly straightforward, because all we need to do is to, use the golden rule. The golden rule states that first we need to find a rule of recurrence. Second, then we have to use measurability. And third, we need to use independence. That's it. Independence, that's it. So for the first part of our golden rule, what we need to do is to, write things in the form of recurrence, that is, of an equation in differences. So what we need to do is to prove that this thing given f, say n, right, equals yn. Again, what we need to do here is to write a time that came before the time which we refer to in here. Okay? And next, what we have to do is just to find the rule of correspondence. So this thing equals what? Well, this thing equals Q divided by P raised to this power. Now, please do note the fact that I am using the same index here as the one that I use here, right? And then what I need to do is to find, okay, this is Q divided by P raised to this power, x1 plus x2 plus so on and so forth, up to xn plus 1. And what I have in here is just an Sn, right? Plus xn plus 1. and that is just Q divided by P raised to Sn plus Xn plus 1, which can be written like this: Q divided by P raised to this power multiplied by Q divided by P raised to Xn plus 1. And now the only thing we have to do is to write this conditional expectation, right? Now, observe that we are talking about just symbols. So we just need to copy and paste all this, right? So what we have in here is that the expectation of yn plus 1, given this story up to this point, equals just the expectation of, okay, yn times Q divided by P raised to this power, given the story up to time n. Oops, I just wrote it horribly. So there we go. And now we have this Fn, that's it. And it's all very simple now, because now that we have used the rule of that we have found this rule of correspondence, which is just a recurrence of order 1, then we can try to use the measurability condition, which says that, well, since we have the story up to time n, then this random variable is actually known to us up to this point. So we can write just yn by means of measurability, right? And then just multiply this by all this information given Fn. And that's it, right? And then we can go forward and use our hypothesis of independence to say that this random variable here is independent of all this story here. And now you might be asking, but why do we know that this random variable is independent of all those random variables? Well, because they just told us that was the case. So we just need to write, well, I'm gonna let this thing go there. And just, okay, write in a different color. Oops, that this is just yn times the expectation of Q divided by P raised to this power, right? And this happens because of the argument of independence, which is why I use this clue notation. Now I need to compute this expectation here, which is actually very simple. So I am going to copy all this. You know, you better do it like that. Okay, yn, like this, times the expectation of Q divided by P raised to this power, right? That's correct, okay? Yes, that's what I had in here, okay? So I'm just writing it again, right? And I have yn multiplied by this raised to the first power times the probability that xn plus 1 equals 1 plus Q divided by P raised to the minus 1 power multiplied by Q. And that is just yn Q divided by P times P. This cancels out with this thing here. And this is just P divided by Q times Q. This thing cancels out with this other here. And I have that P added with Q is just a 1. So I have yn multiplied by 1. And I have yn, which of course, which I wanted to prove. So now for our third exercise, what I have is that again, we have a sequence of random variables which are independent and identically distributed among them, right? Now, they have these couple of features which are common to all of them. They all are worth 0 in their mean, and their variance is just sigma squared, which is a finite real number. Afterwards, we define this sum, which we readily know from our course in risk theory, right? Now, what we have is this definition, this process, which is just this square process minus this other number. And we need to prove that this thing here is a martingale with respect to the information generated by the original random variables. Okay? So the only thing we need to do is to again use our golden rule. So golden rule. First, to find a recurrence rule. Number 2, we need to use measurability. Measurability. Number 3, we need to use independence. To prove what? To prove that the expectation of what? Of yn plus 1 given, given the story up to time n is just this random variable, right? Again, please observe the fact that this time here came before the time to which I'm referring to here. And in order for this to be a martingale, for this process to be a martingale, I have to just put the same time here as the one that I put in here. Now, I need to prove that this thing actually happens. So I'm going to write a question mark in there because I do not actually know if this is true. Well, actually, I do know that it's true. Now, to do this, what I need first is to use my first step of the golden rule. So the first part is to try to write this yn plus 1 in terms of yn, right? Now, what I have in here is that this thing equals Sn squared minus n no? So Sn plus 1 squared minus n plus 1 squared? No, sorry. N plus 1 sigma squared. That's it. So what next? What next? Okay, the following step is just to write that this Sn plus 1 equals x1 plus x2 plus x3 plus xn plus xn plus 1 squared minus n plus 1 times sigma squared, which is just xn plus x1 plus x2 plus x3 plus so on and so forth up to xn, right? Minus 2 times xn plus up to xn times xn plus 1, right? Minus, no, sorry, plus the expectation, plus xn plus 1 squared minus n sigma squared minus sigma squared. And that's it. Because in here, what I can see is that I almost have a recurrence rule, which is given by this thing just equals from this part here. What I see is that this thing is just yn. So I can write yn, right, plus 2 and all these cross products, xn plus 1 minus plus xn plus 1 squared minus sigma squared, right? And what I have to do now is to use this recurrence, right? And in conjugation with measurability and independence to finally prove that what I have is actually a martingale. So let's do it. So what I'm going to do now is to write the expectation of yn plus 1 given the story up to time n as the expectation of yn plus all this. 2 times xn plus 1 times x1 plus x2 plus x3 up to this plus xn plus 1 square, right? And what else? I'm here minus sigma square, and that's it. Oh no, oops, sorry. Given that I have all this story up to this time. And then I just need to observe the fact that this random variable is independent of all this story. Actually, that's where I'm using the proposition which is being quoted here, right? But it doesn't matter. I mean, the only thing you need to observe is the fact that in here I am producing a story which is congruent with what I had in here. So I can just quote measurability once again and say that because of it, I can just take the y process out of the expectation operator and just write this is the same as the expected 2 times the expectation of xn plus 1 times x1 plus up to xn, right? Like this, given fn, right? And then I can just write plus the expectation of xn plus 1 square given fn minus sigma square, because sigma square is just a constant. Now, please observe the fact that, again, I could use measurability in here. You see? Because the story which I refer to in here is just the story that I have in this conditional part. So again, for the sake of measurability, I can just do this. 2, and then x1 plus xn times the expectation of xn plus 1 given fn, right? And then just write the expectation of xn plus 1 square given fn minus sigma square. And then I can use independence, right, to see that xn plus 1 is independent of all this story. And you'll be like, why was that? Well, because all these random variables were independent. Actually, they were pairwise independent. So I can just take expectations here, right? And write xn by independence. xy time plus 2, x1 plus xn times the expectation of xn plus 1, right? Plus, same story here, the expectation of xn plus 1 square minus sigma square. And this is the easiest part of all, because we readily know that the expectation of xn plus 1 equals 0. You see? And you'll be like, but there says that the expectation of x1 is 0. Yes, but they are identically distributed. So if we have the expectation of the first, then we have the expectation of all the others. And we also have the variance, which equals sigma square. So we can just write that this thing equals 0. Then it just cancels with this 2. This thing is just sigma square, which when we take this difference just cancels out. So this thing goes also to 0. And then we have that this is just yn, which is of course what we needed to prove.